I want to present an overview of semiconductor technology. In future videos, we'll go into more detail. Now, we know that human life on Earth is based on the carbon atom that has 4 outer electrons. Modern electronics is based on the silicon atom that also has 4 outer electrons. So we can draw the nucleus of a silicon atom. Let's draw another atom here, an atom here, an atom here, and so on, etc. Now each silicon atom has 4 outer electrons that can be shared with adjacent atoms. So we have two electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, and so on. The structure just, it repeats, and so on, and so on. So we end up with a very stable crystalline structure. For example, if we apply an E field and try and make the charge move, try and generate a current, not much happens. It's a very stable structure. It's a very good insulator, or at least at normal temperatures. If it gets extremely hot, then it can become a conductor. But we can add impurities into this crystalline structure, and we can create 2 different types of silicon. We can create what is called a P-type silicon and what is called an N-type silicon. For example, if we can introduce a boron atom and a boron impurity into this location, the boron atom doesn't have 4 electrons in the outer shell. It only has 3. So we could remove one of these electrons. Now what can happen? In this case, we have an unstable condition. The electron from this atom can go over and fill this spot and leave a vacancy here. Then an electron from another location can move in and fill this vacancy, and so on, etc. So we end up, instead of having an insulator, we end up with charge that can move around. We end up with a conductor. And the more boron atoms we add, the more conduction is allowed. Now, another thing we can do is, let me get rid of our boron atoms. Let's get rid of that boron atom, this boron atom, and this boron atom. Instead of using an impurity of boron, we could put in phosphorus. Now phosphorus, instead of having 4 outer electrons, it has an extra outer electron. So let's say we put a phosphorus atom in here. It has an extra electron that's just sitting there. Now if we apply an E field, this electron can move. So if we add more phosphorus atoms, we add another electron that's sitting out here that's free to move around. So we can change the conductivity. We can make this, instead of an insulator, we can make this a conductor by adding more phosphorus atoms. And so to summarize, we can change the silicon crystalline structure by adding impurities. For example, boron will make it a P-type silicon. Phosphorus or antimony or arsenic, which has 5 outer electrons, will give us a surplus of electrons and make it an N-type material. We'll talk more about P and N-type in a future video. Let's talk a little bit about semiconductor manufacturing. If I have a container that contains molten silicon, and this is the silicon. Now, if I insert a seed crystal of silicon into this molten silicon, and I slowly pull this seed crystal out as I rotate it, what will happen is I will pull out what is called an ingot of silicon. It'll perhaps look something like this. It'll have a certain diameter. This diameter can perhaps be 12 inches or so. Now, I should mention that a small amount of impurity will be added to this silicon molten mixture. For example, if you want to have P-type silicon, you introduce a small amount of boron. If you want N-type silicon, perhaps you'll introduce a little bit of phosphorus. Now, once this ingot is created, it can be sliced into very thin layers. It's like slicing up a sausage. This is like a big sausage. And these little slices are like slices of bologna. So let's draw one of these little slices over here. And we'll call this a wafer, or a silicon wafer. And what we can do is we can manufacture many hundreds or thousands of chips on this wafer. They're all manufactured together at the same time. For example, one of these squares may be a chip. And these chips can contain millions, even billions of electrical components, or transistors. Now, these transistors, or these components, are made by changing the regions within this chip, by changing regions to P-type and regions to N-type. These electrical components can be manufactured. Let's talk a little bit about these P-type and N-type regions. For example, if I have a P-type region and I put it next to an N-type region, this is N-type, at the interface something rather strange happens. We create what's called a depletion region between the N and the P-type silicon. It has very special properties, and we'll talk more about this in a future video. But right now I just want to give you an overview. So when we put a P-type region next to an N-type region, we get an electrical component that we call a diode, and this is a symbol for the diode. The diode allows current to flow from the P side to the N side in this direction. And it blocks current flow in the other direction. Now, if we take a PN region, say this is the P region, this is the N region, and we add another P region, we get a bipolar transistor. That's a PNP type transistor, and this is the symbol for it. This is called the emitter base collector, and this part of the P region would be the emitter, this part would be the base, and this would be the collector. Now, if we arrange these P and N regions a little differently, for example, if we have an N region that connects to a P region that connects to another N region, we get what we call an NPN transistor. And its symbol looks like this. In this case, this is what's called the emitter, the base terminal, and the collector terminal. So this would be the emitter, P region would be the base, and this other N region would be the collector. Now, we can create different kinds of transistors on a silicon chip. For example, if we take the surface of the wafer and we introduce an N-type region and another N-type region, this is N-type, N-type. We'll say the wafer is P-type. So the wafers, say this is the thickness of the wafer. If we put an insulating layer above this center region and put a conducting region here, we form what we call a MOSFET transistor. And its symbol is like this. And this, because this region is N material, we call this an Nmos transistor. This is called the gate. This material up here is called the gate. This can be called the source, and this region will be called the source. This will be called the drain. This will be called the drain region up here. Now, if we construct this transistor a little differently, we can again take the surface of the wafer, and instead of putting an N region in, we could put in a P region and another P region. Well, this has to sit in an N region. So we'll have an N region that this device sits in. This is N-type. There'll be an insulating layer. And on top of that insulating layer, we'll put this electrode, which we call a gate, which is this material. Now this forms another type of MOSFET transistor that we call Pmos. And its symbol looks a lot like the Nmos, but we put a little bubble here. So this is the gate, and this up here is the gate. This we can call the source. So this P region here would be the source. This we can call the drain. This P region here would be the drain. So hopefully this gives you some overview of the semiconductor technology, and we'll go more into each of these diodes and transistors in future videos. Very good insulator, or at least at normal temperatures. If it gets extremely hot, then it can become a conductor. But we can add impurities into this crystalline structure, and we can create two different types of silicon. We can create what is called a P-type silicon. It repeats, and so on, and so on. So we end up with a very stable crystalline structure. For example, if we apply an E field and try and make the charge move, try and generate a current, not much happens. It's a very stable structure. Each silicon atom has 4 outer electrons that can be shared with adjacent atoms. So we have two electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, and so on. This structure just electronics is based on the silicon atom that also has 4 outer electrons. So we can draw the nucleus of a silicon atom. Let's draw another atom here. an atom here, an atom here, and so on, etc. Now, I want to present an overview of semiconductor technology. In future videos, we'll go into more detail. Now, we know that human life on Earth is based on the carbon atom that has 4 outer electrons. Modern